Good afternoon. My name is Nolan, and today I'm going to be presenting random access hardware sequence compression, which was a joint effort by myself, Yoon Lee, Gagan Panwar, and my advisor, Steve Jin. In mid-2025, DRAM already represented 40 to 50% of cloud server infrastructure costs. And since then, the price of DRAM has nearly tripled in only a year due to uh, tons of AI demand. And as DRAM approaches its physical and economic limits, significant interest has turned to approaches that reduce the memory footprint. So as a quick primer on one of these very promising solutions, here's how hardware memory compression works. So in a normal system, the installed DRAM matches the DRAM capacity of the system, but under hardware memory compression, you insert a small hardware compressor and decompressor into the memory controller, and data is compressed by that hardware before it's stored. And this can give you an effective memory capacity that's dramatically larger than the installed memory, in this case, 4 times as much. So there are several examples of capacity-oriented hardware memory compression in both industry and academia. And it's common in these systems to tier DRAM into a compressed and uncompressed tier. This type of memory system is the setting for this work. And you can see that on the left side, the processor sees a large physical address space, but on the right, the actual DRAM is much smaller. And hot pages, frequently accessed pages, are put in this uncompressed tier and suffer very little overhead, while colder pages are compressed and packed into this compressed region of memory. So what type of compression algorithm do many of these use? And I wanted to draw attention to the OCP hyperscale tiered memory expander specification, which actually mandates the use of LZ, specifically a type of compression, a sequence compression algorithm that operates at 4 kilobyte granularity or a standard memory page. So why was page level sequence compression mandated? The short answer is just that page level sequence compression gets the highest compression ratios out of all prior hardware accelerated compression work. You can see in the graph that on the x-axis we have the compression granularity, which is the data unit that gets independently compressed at one time. And then on the y-axis we have compression ratio, where 1 means uncompressed and 4 means very compressed. And on top you can see that page level sequence compression really far outperforms the memory block level compression algorithms that are more targeting latency. But this work is targeting maximum capacity. So we're really looking at these page level sequence compression works. And our baseline is ASIC deflate. And we're going to be comparing against that several times. And I also just wanted to point out that these benchmarks, these 7 suites and these 88 dumps, we're already removing 0 pages. So page level sequence compression is necessary for aggressive hardware memory compression. And the next natural question is, what is sequence compression and how does it achieve these high ratios? So a sequence is any 2 or more contiguous bytes. And the workhorse of most of these, or actually all of these sequence compression algorithms I showed on the last screen is LZ. And the way that LZ works is it looks for a match of a prior sequence, and it usually encodes this with a pointer. In this case, the 3-2 represents look 3 bytes back, copy 2 bytes. And this can just go on until you have properly compressed the data. And you can see how this can be just very, very efficient at eliminating redundancy in data. So A consequence of this approach, though, is that without prior context, the decompressor can't decode the pointer from anywhere besides starting from the very beginning. So that's why under these works, typically compression or decompression starts at the very beginning of the compressed page and has to proceed serially through the page. So this is how it's a problem. I have this quick example here where a cold memory page is being compressed by an LZ compressor, and then it goes to compress DRAM, and everything is fine until there's a memory request. And then while this block is potentially stalling the pipeline, the processor has to wait for this maybe over a kilobyte of data to be fetched and then serially decompressed by the decompressor before the memory request can be served. And both of these are a significant source of latency. Um, so if we take a closer look at the compressed page, you can see that all prior data to the block that we care about is acting like a dictionary to compress this block and must be fetched and decompressed to prior. So a naive solution to fix this issue with the fetch and decompress is by restricting these pointers to just a small region in the beginning of the page. And the benefit of this is if we have that same request, all we need to do is fetch those two memory blocks and the compressed block. And then because the only dependencies are on that region in the beginning of the page, we're able to decompress just what we need. But unfortunately, this has a significant degradation on the compression ratio, where it falls from around 3.3 with no restrictions on the dictionary size down to about 1.75, which is a lot less when you think about the effective expansion. So while this gives us a blueprint to achieve random access to some degree, the key point and the key challenge is that we need to dramatically increase the efficiency of how we store these sequences in that dictionary so that we can still have similar compression ratios. And to make this just very concrete, our goal is to achieve random access via a small dictionary, but also match the compression ratio of ASIC deflate. And you can see that we're trying to reduce both this fetching overhead in terms of latency and then also the decompression computational latency itself. So the next natural question is which sequences should go in this small dictionary? And I have this abstract example that builds some intuition for how we should go about selecting sequences for this dictionary. If we choose sequence A, you could see that we achieve some savings in the size of the page where the purple sequences have become these small sequence identifiers. And alternatively, we can choose sequence B, and you can see that it actually yields the same amount of savings, but sequence B is physically shorter in terms of data, so we can actually store more before we end up reaching our dictionary size budget. And you can see that sequence B ultimately was a better choice because all things equal, it was smaller and therefore we can pack more sequences in. So the key idea for this work is given this limited dictionary size budget, how do we make best use of this space? And the idea is that we can quantify how good a sequence is using a metric called utility, which just weighs the benefit against the cost, where the benefit is the savings and the cost is the size of the sequence. And we call this RST, or randomly decompressible sequence compression with top utility selection. So to achieve this, we have to design a new competing sequence compression algorithm to LZ and a new accelerator for that compression algorithm. And from the ground up, this algorithm is designed to maximize the utility of the dictionary. So first, RST takes this example page, and it's going to find all of the sequences up to length 5. 5 is there's a trade-off between the max sequence length and the compression ratio and the computational complexity. The details are in the paper. And you can count up how many of each of these sequences occurred in the page, and then you can calculate their utility values. And in this case, XY is the top utility sequence, so it's added to the dictionary. So here's a high-level architecture diagram of the compressor, and I could talk about the various data hazards and the various parallelization challenges that we solved in the paper, but I think it'd be more fun to go through an example. These all have various parallelization challenges and need to be massively parallel to keep up with the huge volume of utility calculations that you need to do during this sequence selection step. But I'll just go through this example now. So you can see the same input as before. And first, the sequence count module is going to count up every occurrence of the sequence, and it's going to put them into a banked SRAM. And you can see that there's 4 occurrences of XY, etc. And the top utility sequence is chosen and added to the dictionary. And then the substitution module completely in parallel will match and substitute all occurrences of the sequence. And then next, we want to be able to select the next sequence, but the utility table is currently stale. So we have an update generator module that will go substitution site by substitution site and create increment and decrement records to figure out exactly how precisely to adjust the stored count values such that they match the actual data. And you can see that once this is done, the count of XY, which no longer exists in the page, has gone to 0. And if we turn our attention to the bank 2, we can see that there's a new sequence that previously didn't exist in the page, Z1 star Y, that now exists in the page, and that actually happens to be the top utility sequence. This is added to the dictionary, and because everything is still symbol aligned, byte aligned, you can substitute again, and this can repeat iteratively until you run out of dictionary space. And this is just showing that alternatively, once there's no more sequences, it can end. So once the main compression stage is over, you can assemble your compressed page by putting the dictionary in front of these compressed tokens. And now we can decompress. So here I'm showing an example where we're decompressing just the second half of the page to show this random access capability. This is something that would be impossible with deflate or any LZ algorithm. So first, you can partition the compressed block across multiple of these LIFO expanders, and the dictionary gets expanded. And the way that each of these works is it just operates like a stack. If there's a compressed token, then it will consult the dictionary table. And if there's a literal on the top of the stack, it'll just pop the output. So you can see how this can create the final compressed token. And you can see that after that, we can just concatenate the output. So this is another thing that the algorithm allows, because everything's totally independent and the dictionary is the only single source of truth for how these expansions should go. You can, even within the decompressor, use a lot of parallelism. And compared to the original compressed page, you can see that we correctly reconstructed just that second half. So in reality, this would be a compressed block if the example was longer. So in terms of how this work does in terms of compression ratio, you can see that against our baseline ASIC deflate, in some categories we do slightly better. Specifically, text RST is slightly worse at, but for most benchmarks, it does about the same, and we do slightly better at C and C++ benchmarks. And then now for the hardware synthesis results. So this, I implemented this in System Verilog, and on a 7 nanometer tech node, you can see our synthesis results, and I wanted to draw attention to this decompressor area where we just dramatically reduce the computational latency compared to ASIC deflate by a factor of about 8. And the amount of overhead accesses becomes just the dictionary instead of the first half of a compressed page on average. And then the trade-off is that RST's compressor throughput is significantly lower. And this is actually something that works slightly in our advantage because we've shifted all of the work to the compressor where things are not on the critical path, and we've made it as easy as possible for the decompressor, which actually is stalling the CPU and is on the critical read path. So our system level evaluation was done with Gem 5, and you can see that on these benchmarks, we had an average of 15% average application speed up over the ASIC deflate baseline. And this is excluding read stride 1K, which is a stress test, that a micro benchmark that is showing that there's potential with lots of compressed accesses to get up to 5x speed up. So our takeaways are that top utility selection is able to distill an entire page's worth of sequence redundancy into a very small 128 byte dictionary, and thus allows for random access of individual compressed blocks. RST shifts dictionary construction off the critical path by focusing all of the computational complexity of dictionary construction on the compressor. And RST cuts decompression latency from 140 nanoseconds to 18 nanoseconds, improving application performance by 15% versus prior art. And we have functional RTL on GitHub and our Zenodo for the artifact evaluation. And my collaborator, Yoon, made this beautiful RST visualization that also has some samples. And later we'll be releasing the full generator if you want to try it yourself. And you can see that it splits up it into the dictionary entries and then the expanded dictionary entries that show that a single iterated sequence, a single token can represent a very long sequence after several iterations. So thank you, and I look forward to any questions.
Hi, Javid from Meta. Brilliant work. Thank you. Amazing. Compared to just very basic traditional dictionary compression or decompression, where you could just come up with a large dictionary that's common across your population of your data. How do you compare? Were you able to see differences in compression ratio and advantage of having your live dictionary being built per page? Do you follow my
So I guess, are you comparing to like an offline dictionary
just
construction?
offline, massive dictionary based?
So your compression can only be as good as your prior, like how well you understand the nature of the data, and memory data can be extremely diverse, right? And we found that if you try to have a dictionary serve a single one that serves lots of data, the compression ratio just tanks. So you have to have this dynamic adaptation per page, and that's where all the efficiency is. So there are some potential with offline training, but for this work,
do you have that data to later upload it somewhere? Like, versus the size of a dictionary, like you could go with 64 kilobyte, 128
I have.
kilobyte, and
So RST is actually so efficient at mining sequences that the ratio really kind of plateaus fairly quickly because most of these sequences have already been distilled, and then you're just getting this long tail of additional compressions. So you can train one or many of these dictionaries, but that's not the deployment setting that we were looking at, since every memory page is isolated in under this.
So you don't have something similar for a global dictionary, like a global. You don't have.
Yeah, nothing with that yet. That's a very interesting direction, though.
Your work is very interesting. Hello, I'm Fei Yang from NC State. So I want so can you go back to the page where your case study? So I wonder, like
The
you said,
case
you only
study.
have to decode the case study, the small example one.
Oh,
You said that you only need to decode the second part because of the dictionary things. I wonder, since like your dictionary seems to be a run length problem, how do you actually know that which part you need to decode?
oh, so how do you access the compressed block?
Yes. So like you said, you only need to decode,
Oh,
uncompress the
okay.
second part.
So I actually, this is also backups. I cut this mostly for time reasons, but we actually in the paper go into detail about how you can locate the compressed block
Okay.
and how you can do so efficiently with very little metadata. So we have a 1-bit offset that represents whether the prior compressed logical block is in the same physical block or in the next physical block. And then we have an offset in the beginning of each compressed block that allows you to find the start of the first compressed logical block within that compressed DRAM block.
Okay.
That's in the paper.
So you're basically using some sort of indexing to map the run length compression so that you could access them within constant timing.
So RST is actually a little more powerful than traditional run length in that it can hierarchically build any sequence.
Okay.
It doesn't have to be a run that's repeating like an LZ
This
run.
one actually kind of remind me of an algorithm called sequitur. I don't know.
Sequitur.
Sequitur.
Yeah.
Which is also a hierarchical in run length encoder that can just build a context-free grammar tree.
Yes,
So
exactly. This is in the same family.
Of that, since you're like at the beginning of your presentation when you show the LZ things, but then I thought to myself that then the encoding would be run length and you would be hard to have like a constant time sorry, your constant time access random access because you potentially need multiple jump to reach your compressed sections. So how do you actually deal with that?
Yeah, so we actually use the same system as dialect, which is prior work in terms of finding the compressed page, because there's an additional layer of translation between the OS physical memory and the compressed physical like DRAM memory, right? But on top of those compressed table entries, we're now adding this location dictionary, which is what I have listed as offset here. And then that allows you then to most of the time not incur any overhead trying to access this additional location metadata to find the compressed block. So in the common case, you already actually have this extra 8 bytes and you can know exactly where the dictionary is and what the compressed block location is, and you can fetch them in the same round trip.
Thank you. It's very interesting.
Thanks.
Okay. On good. Martin Promer, Spiral, though in a past life I was database faculty at Carnegie Mellon. Have you looked at shared dictionaries with like Z standard, etc., just to kind of scope it? Two, very recent work in database space that is highly adjacent, that you may or may not have seen. Just curious if it's on the roadmap and possibly could be aligned to collaborate on. FSST, fast static symbol tables, or like on pair compression. So curious if any of that means anything to you.
So for your ZSTD question, yes. So ZSTD uses cover or a faster version called algorithm called fast cover to build its dictionary, and these dictionaries are by default 110 kilobytes versus our dictionary, which is very small and trained online.
Yeah.
So we have looked into it. LZ just isn't super amenable to small dictionaries because it doesn't know when it selects a sequence whether it will win out or not eventually when it does the parse, right? So that's something that we did look into, but it's a different enough deployment environment that we haven't really done more than just measure and characterize it. And this, like you said, FSST.
Yeah.
Yeah, we can talk offline about that. I don't know what that is.
Yeah, wonderful. Thanks for the amazing talk. Looking forward to chatting. Thank you.
Hello. This is Song Young from Meta. I have a few questions regarding this, and Thank you for the great talk. I I think LZ-based compression may not work for every applications. So I wonder how are you gonna handle this? Like, are you gonna turn on and off, or what will be the real application you can apply this strategy for that?
Sure, that's a great. Oh, whoops. I guess I'm. So yeah, you can see that these are the benchmarks that we were looking at, and yeah, like it doesn't cover AI, and the reason for that is because deflate or other sequence compression works don't tend to have very high compression ratio on floats, and generally algorithms that specifically compress the exponents of those floats tend to do better on those types of dumps, but that's just not, you can see that there's a lot of domains that it does very well. Pure numerical or AI workloads, that's one area that future work will explore.
Okay, thank you.
Thanks.